Hi everyone, I'm Luca Reali, an undergraduate student at the University of Milan, and in this video I'll be talking you about our recent work where we developed a procedure that allows us to span the entire evolutionary history of a precessing binary black hole from the asymptotic configuration at past infinity to its merger remnant. Our results are scale-free, meaning that they are valid both for stellar mass binary black holes in the LIGO-Virgo band and for the supermassive binary black holes targeted by LISA. In this second case, relating the properties of a merger remnant to the dynamics of its progenitor can be of particular astrophysical importance because supermassive black holes are believed to grow hierarchically together with their host galaxies. Now let's get into the details of our work. So let's consider a spinning binary black hole on circular orbits. Now here we focus on two spins effects, so we consider black holes of comparable masses and that are both spinning. So as the two black holes orbit about each other, the three angular momenta of the system, the spins of the two black holes and the orbital angular momentum, are all coupled to each other and precess, while the orbital separation gradually shrinks due to the emission of gravitational waves until the two black holes finally merge, producing a black hole remnant. Now, in the limit where the orbital separation goes to infinity, it can be shown, and if you want more details about this, you can check this paper right here. It can be shown that a precessing binary black hole is completely characterized by a set of 5 variables. The mass ratio Q, the spin magnitudes chi1 and chi2, and the two spin angles θ1 and θ2 infinity, which are the asymptotic values of the angles between the spins of the two black holes and the orbital angular momentum as the orbital separation goes to infinity. On the other hand, a merger remnant is fully described by its final mass mf, its final spin kf, and its recoil velocity vf. So what we did was putting together multiple layers of post-Newtonian evolutionary techniques to describe the inspiral with a recent and very accurate numerical relativity surrogate model to predict, to estimate the parameters of the remnant. So I won't enter too much into the details of the post-Newtonian techniques we employed, but I'll just sketch them briefly here. So in the regime where the post-Newtonian approximation holds, meaning as long as we consider orbital separation way larger than the gravitational radius, the three typical timescales of the system are widely separated, meaning that the radiation reaction time, the typical timescale in which the orbital separation shrinks, is way bigger than the precessional period, which is in turn way larger than the orbital period. Now, in the literature, this timescale separation has been exploited to develop basically two kinds of post-Newtonian techniques. The well-known orbit average approaches, where one averages quantities over the orbital period and then evolves those average quantities throughout the spiral, and the more recent precession average approaches, where one double averages quantities over both the orbital and the precessional period, and then evolves those quantities on the biggest timescale of the problem. Now, clearly, an orbit average technique is not capable of keeping track of the evolution of the binary along each single orbit. So in order to evaluate our surrogate, we need to sample a random parameter, the orbital phase, which we extract uniformly between 0 and 2 pi. In the same way, a precession average technique is not capable of following the evolution of the system along each precession cycle. So we need an additional random parameter, the precessional phase S, which again, without entering into the details, is sampled according to a probability distribution that behaves like this. So it's highly peaked at the extrema of the allowed range for the precessional phase. So we combine these two kinds of techniques, and here's a scheme of the procedure we came up with. So first of all, we pick a certain binary configuration at infinity. We evolve the binary using a precession average approach up to a certain threshold in the orbital separation. Here we sample the precessional phase S and we switch to an orbit average approach. We then evolve our binary with the orbit average technique up to another threshold, this time in the orbital frequency, just because of how the numerical relativity surrogate model works. Then we sample the orbital phase and we evaluate our surrogate to estimate the remnant parameters MF, KF, and VF. Now, the random sampling of these two phases, the precession and the orbital phases, naturally introduces some uncertainties on the predictions, on the estimates of the remnant parameters. But we argue that actually any astrophysical model that aims to connect the remnant parameters with the properties of its progenitor at astrophysically large separation has to deal with this kind of uncertainties, because the black holes complete a huge number of precessional cycles and orbits before they actually merge. So our procedure naturally allows us to study the impact of these uncertainties on the predictions of the remnant parameters. And that's exactly what we did. So here we consider a certain binary configuration at infinity, and we evolved it 1,000,000 times using our procedure, each time sampling different values of the precessional and the orbital phases and computing the corresponding remnant parameters MF, KF, and VF. And here we plotted the resulting distributions in the remnant parameter space. So as we can see, a given binary configuration at infinity is not mapped into a point, but it's actually mapped into a region in the remnant parameter space due to the phase sampling uncertainties we discussed before. And the width of these regions allows us to provide order of magnitudes estimates of these uncertainties. So for this specific binary here, we can see that the uncertainty, the error over the final mass, is basically negligible to all practical purposes, 0.1%, while the uncertainty on the final spin is significant, and the error over the kick velocity is huge. And this is because the recoil velocity is heavily affected by the exact configuration of the system at merger, and in particular by the exact value of the orbital phase at merger. So this plot here was obtained by sampling over all our sources of uncertainty, but then we wanted to disentangle the different contributions. So here we considered the very same binary as before, but this time we picked a fixed value of the precessional phase and we sampled only over the orbital phase, obtaining these two loop structures in the remnant parameter space. Now the loops are colored according to the value of the orbital phase, while the dots are obtained just by sampling also over the Gaussian errors of the surrogate, only to show that these numerical errors are small compared to the physical uncertainties that we are considering here. So as we can see, there is an exact 2π periodicity in the orbital phase, and this was to be expected because the remnant parameters are 2π periodic in the orbital phase by construction. But we have two loops, so we can see there is also an approximate π periodicity, and this is related to the symmetry of the system, because a completely symmetric binary that is a binary with equal mass, equal spin black holes, would manifest an exact pi periodicity, so only one loop in the remnant parameter space within the numerical errors of the surrogate. While for a generic binary, a more generic binary like this one, the pi periodicity is broken and we see a more complicated structure. So this was obtained by fixing the precessional phase, but what happens if we change it? So here we repeated the same procedure as before, but in each line of this plot we pick a different value of the precessional phase. So we can see that varying the orbital phase while fixing the precessional phase makes you move along one of these two loop curves, while changing the precessional phase makes the loop move in the remnant parameter space, gradually covering these regions here. So these regions are formed by a continuous superposition of an infinite number of these loops. So all of this was obtained for a single binary, but what happens if we change the binary parameters at infinity? So here we consider different binary populations at infinity with different distributions of the parameters q, k1, k2, and θ1, θ2 infinity, and we plotted the corresponding distributions of the errors over the remnant parameters mf, kf, and vf. So as we can see, the errors change as we change the binary configuration at infinity, meaning that they are not fixed for every binary black hole. But in any case, the statements that we made for the specific binary we considered before can be generalized. So the errors over the final mass in general are negligible to all practical purposes. The errors over the kick velocity are huge, while the uncertainties over the final spin are of order from 1 to 3%. And so here, just to show off a little bit more the potential of our evolutionary procedure, we consider a certain binary population with this fixed value of q, k1, and k2, and then we exploited our procedure to map the entire θ1 and θ2 infinity plane into the mf, kf parameter space. And actually the entire θ1, θ2 plane is mapped into the gray background area right here. Then the colored dots are a sample of 30 binaries uniformly distributed in the θ1, θ2 plane, and each dot is mapped into the corresponding colored region by our procedure due to the phase sampling uncertainties we discussed before. And both the dots and the regions are colored according to the value of the projected effective spin psi, which is better known in the literature as chi effective. And this was to show a correlation, to highlight a correlation between the final mass and the final spin of the remnant that is due to the well-known phenomenon of the orbital end gap. Basically, a binary black hole whose spins are mostly aligned with the orbital angular momentum, for a system like this, the merger occurs later, and so it tends to produce a remnant with higher spin but lower mass, and vice versa. And we find that the projected effective spin is a good parameterization of this correlation because it is a measurement of spin alignment. So to sum up, we developed a procedure that allowed us to connect the two extrema of the evolution of a precessing binary black hole and to assess the impact of the unavoidable uncertainty that necessarily affect astrophysical models that aim to connect the properties of the merger remnant to the dynamics of the parameters of its progenitor at large separation. And we found that the errors over the final mass are basically negligible, while the errors over the final kick, the kick velocity, are huge, and the errors over the final spin are of order 1%. So thank you for your attention, and I hope you enjoyed this talk.